So my name is David. I'm going to be presenting tonight's lecture. So we're going to go over alcohol, carboxylic acids, and some reactions specific to them. And my name is David. So I just wanted to go over the recording again. So we are recording this lecture, and then we will post it to YouTube as well. So if you don't want your picture, your profile picture, or your full name in the recording, if it happens to be in there, you can change that now. But if you are in the Zoom meeting, then you are consenting for us to record everything in this lecture. So just a quick course description. We are doing a 15-week MCAT course. So we do lectures on Zoom every Thursday, Friday, and Saturday night at 8:30 p.m. EST. And then on Sundays at 8:30 p.m. also, we do office hours. So if you have any specific questions or problems you want to go over, we can help you then. And just some links for you. So we have a group me. If you are not in the group me right now, there's a few hundred other students in there. So if you want to ask any questions or ask for advice, you can do so. And like I said, we do have a YouTube channel where we post the recordings, and then we also cut up the recordings into little 10-minute clips on specific topics if you want to check those out. And we have our website, socraticmed.net. So if you want to take a look, we do post the recordings on there as well, and the little clips, and then just some general information about the program. And also the Instagram, if you want to follow it, they give like daily updates about what we're doing and remind you about lectures and stuff. So just some learning objectives for today. I'm going to review the reactions involving alcohols. I'm going to go over what a phenol is and some reactions with them. And then finally, I'm going to go over some carboxylic acid reactions and how to form the other carboxylic acid derivatives from carboxylic acid. So first off, I'm going to go over alcohols. So just some general information about alcohols. They have the formula ROH with the OH hydroxyl group, functional group. So on the bottom, I just have a picture of a general structure of an alcohol. So the R group is usually a carbon chain attached to this OH group, which is the hydroxyl group, and that's the defining feature of alcohols. So alcohols, they're capable of intermolecular hydrogen bonding. So this leads to higher melting points and boiling points compared to normal hydrocarbons. And molecules with more than one hydroxyl group, so the diols, they'll have a greater degree of hydrogen bonding just because there's two hydroxyl groups that are able to hydrogen bond. And the hydroxyl hydrogen, so this hydrogen attached to the oxygen, is weakly acidic. So alcohols can dissociate into H+ ions and also alkoxide ions, similar to water. So they can split up into the H+ H+ proton, and then the OH- that is usually attached to this R group carbon chain. So that's just some general information about alcohols. Next, I'm going to go into the oxidation of alcohols. So alcohols, they're the most reduced form of a carbon bonded to an oxygen. So we are able to oxidize these alcohols. And the first reagent, pyridinium chlorochromate, or mostly known as PCC, it's a mild anhydrous oxidant. So what this means is it is able to oxidize primary alcohols to aldehydes and secondary alcohols to ketones, but it is not able to hydrate aldehydes into carboxylic acids because it lacks H2O. So the anhydrous part, it means it lacks H2O, so it's unable to hydrate aldehydes into carboxylic acids, unlike the other groups, the other reagents that I'm going to go over later. So this is a pretty weak oxidizing agent, but it is able to oxidize alcohols into carbonyls. So as you can see in the picture on the bottom right, the first tertiary alcohol after using PCC, the oxidizing agent, it is able to form a aldehyde. And then for secondary alcohols on the bottom, after using PCC, it's able to make a ketone. And just as a general rule, you can't oxidize tertiary alcohols because they're the most oxidized it can be without breaking any carbon-carbon bonds. So we can oxidize secondary and primary alcohols, but not tertiary alcohols. So just for PCC, just know that it is not as strong as the other oxidizing agents. So it is only able to oxidize into a carbonyl. So primary alcohols into aldehydes, and then secondary alcohols into ketones. But like I said, any oxidizing agent that you encounter on the MCAT that's stronger than PCC, they will be able to oxidize secondary alcohols to ketones as well. But then for primary alcohols, using a strong oxidizing agent, it will be able to produce a carboxylic acid. So just a few oxidizing agents that you might encounter on the MCAT: sodium dichromate, Na2Cr2O7, and then also potassium dichromate, K2Cr2O7, and lastly, potassium permanganate, KMnO4. So these are all strong oxidizing agents that can oxidize secondary alcohols to ketones similar to PCC. But then for primary alcohols, instead of oxidizing it only to an aldehyde, it will oxidize the alcohol into a carboxylic acid if it's a primary alcohol. So these are strong oxidizing agents. As you can see on the bottom, it can oxidize molecules to form a carboxylic acid. So as you notice in these three oxidizing agents, one key feature is to have a lot of oxygens in them. So just as a good rule of thumb, if you see any agents with lots of alcohols in them, they'll most likely be an oxidizing agent because oxygen is a pretty electronegative element, which would want to oxidize the reagents. So that is oxidation of alcohols. And then another form of oxidation is called Jones oxidation. This is when it uses chromium trioxide as an oxidizing agent. So CrO3 is the formula for chromium trioxide. So in this reaction, the chromium trioxide is dissolved in dilute sulfuric acid in acetone, and it functions similar to those strong oxidizing agents where it oxidizes primary alcohols to carboxylic acids and then secondary alcohols to ketones as well. So any questions on this before we go into a problem? You can put in the chat or just unmute. And also Chris, another tutor, is with us today. If you have any questions during the lecture, you can put it in the chat and he can help you out. Okay. If there's no questions, let's try out this question. The oxidation of primary alcohols can produce which of the following pairs of products, depending on the reaction? So let me start the poll and I'll give everyone a few minutes for this. All right, take a few minutes to answer this question. So Syed asked, do you need to know the detailed mechanism for these reactions? No, you don't need to know like specifically how the mechanism works. You just need to know if you're given a specific reactant and then an agent, what happens, what would the product look like? It would be helpful to know the mechanisms, but you definitely don't need to know the detailed mechanisms for the MCAT. And Ash, today's lecture is on alcohols and carboxylic acids. All right, I'll give everyone a few more seconds on this question. If you want to put in your answer, all answers are anonymous, so take your best guess. All right, I'm in the poll in a few seconds. Okay. Most people pick choice A, and yeah, that's the correct answer. So for this question, it asks, if you're given a primary alcohol, what products can you form depending on the reaction? So depending on the reaction, you could form different products. So if you're given a primary alcohol, you know, if you use PCC on it, that will form an aldehyde because PCC is not a strong oxidizing agent, so it won't be able to form carboxylic acids. But any other reagents like potassium dichromate or sodium dichromate, any of those stronger oxidizing agents, they will be able to form carboxylic acid when reacted with a primary alcohol. Any questions on this before I move on? Okay, all right. So next, I'm going to go over protecting groups for alcohols. So the hydroxyls of alcohols, they are poor leaving groups for nucleophilic substitution reactions. So for nucleophilic substitution reactions, you usually need a good leaving group in order to kick it off, but hydroxyls aren't great leaving groups. So what we usually do is they can be protonated and reacted in order to form better leaving groups, and those leaving groups are called mesylates and tosylates. So in this reaction, the alcohol acts as a nucleophile and it's converted into an ester, a type of ester called sulfonate. And sulfonate ions are weak bases, so they make excellent leaving groups, and that helps when you're doing a nucleophilic substitution reaction. But they can also be used as protecting groups for alcohols against oxidizing agents. So if you convert an alcohol into a mesylate or a tosylate, you won't, if you use an oxidizing agent like BCC or anything against it, it won't be able to oxidize it. So first thing, mesylates, so they contain the functional group SO3CH3. So instead of OH, instead of an OH, you replace it with an SO3CH3. And this is prepared using methyl sulfonyl chloride and an alcohol in the presence of a base. You don't need to know the really the specific reaction or how it works, but just know what happens when you convert into mesylate and kind of what the general reaction looks like. So when you convert to a mesylate, it becomes a good leaving group in a nucleophilic substitution reaction, but also you can use that as a protecting group against oxidizing agents. Tosylates are similar, except it has a different structure. It has the formula of SOC6H4CH3. And similarly, you react an alcohol with p-toluene sulfonyl chloride in order to form an ester called toluene sulfonic acid. So both methylates and tosylates, they're called sulfonate ions, and they're used as protecting groups for alcohols. And then similar kind of alcohols can be used as protecting groups for other functional groups like aldehydes and ketones. And this is to prevent reduction by reducing groups. So when you react an aldehyde with two equivalents of alcohol or a diol, so a molecule with two alcohol groups on it, you form an acetal. These are primary alcohols with two OR groups and a hydrogen group attached to it. So this would not be able to be reduced by a reducing group or a reducing agent. So this is to protect the aldehyde from being reduced back into an alcohol. And similarly, if ketones are reacted with two equivalents of an alcohol or a diol, it forms ketols. This is a secondary alcohol with two OR groups attached to it. And similarly, it's used to prevent reduction by reducing groups. And if you want to get rid of the protecting group, or otherwise known as deprotection, in order to convert it back to a carbonyl, you react the molecule with aqueous acid in order to kick off the alcohol or a diol in order to get your ketone or aldehyde back. And this is just to show how that reaction works. So you can see there's a carbonyl on the ring, and when you react it with this diol, it forms this pentagon-looking group, and that protects the ketone from being reduced. And when you react it with acid, it converts it back to a carbonyl group. Sorry, it says I'm being kicked out of the Zoom, so hold on one second. Sorry, hold on one second. Sorry about that. Hold on one second. Let me just pull up the lecture again. Okay. Yeah, so that is protecting groups for alcohols. Next, I'm going to go into phenols. So phenols, they're hydroxyl groups attached to aromatic rings. So they're alcohol groups that are attached to like a benzene ring. But one difference is these hydroxyl hydrogens, they're more acidic than normal non-aromatic alcohols because of the resonance within these rings. So normal like straight chain non-aromatic alcohols, the hydroxyl hydrogens are just weakly acidic, but these hydroxyl hydrogens on the ring, they're more acidic because the aromatic ring allows resonance stabilization of the negative charge on the oxygen once the hydrogen or proton leaves. So that stabilizes the anion that's formed after the hydrogen leaves. So on the bottom, as you can see here, once the hydrogen is kicked off, the negative charge on the oxygen, it can be resonated throughout the ring. And this resonance leads to a more stable anion, and that causes the hydroxyl hydrogens to be more acidic on the phenol ring instead of when compared to non-aromatic alcohols. And so one reaction involving phenols, so when you oxidize a phenol with oxidizing agents, it forms a group known as a quinone. And this quinone is stabilized by resonance due to the conjugated ring system. And so some after oxidation still have aromatic rings, but not always. So as you can see on the bottom, this reaction of a phenol with an oxidizing agent, it forms this quinone, and it's stabilized by resonance due to the conjugated ring system. And the ring began as a aromatic ring, but after oxidation, it's not aromatic, but some may still be aromatic after oxidation. And hydroxyquinones are similar to quinones. They share the same ring and carbonyl backbone as quinones, but they differ because of an addition of one or more hydroxyl groups. So this leads to, it's similar to a quinone, except it's further oxidized. So on the bottom, as you can see here, these hydroxyquinones, they kind of look like the quinones, but they have extra hydroxyl groups attached to it. Any questions on this before I go into carboxylic acids? Sorry, let me look in the chat. You can put in the chat or just unmute. Okay. All right, I'll move on to carboxylic acids. So carboxylic acids, on the right, I just have the general structure of one. They have a carbonyl group and a hydroxyl group bonded to the same carbon. This is a terminal group and usually the most oxidized functional group on the molecule. And because of the acidic hydroxyl hydrogens attached to that oxygen, it's able to hydrogen bond with other molecules. So this is a pretty reactive molecule. On the right, you can see here, attached to the carbon is a R group, usually in like an alkyl chain. Then it's also attached to a oxygen through a carbonyl, and also attached to a hydroxyl group via a single bond. So there are a few ways to make a carboxylic acid. One of the ways is through the oxidation of aldehydes or ketones using a strong oxidizing agent, or a primary alcohol as well. So if you take a primary alcohol, an aldehyde, or it shouldn't say aldehyde and ketones, it should say aldehydes and primary alcohols. So as you can see on the bottom, if you take a primary alcohol and react it with potassium permanganate, you get a carboxylic acid. And similarly, if you take a aldehyde and you react it with a strong oxidizing agent, you can form a carboxylic acid as well. And on the bottom is just a representation of how to react a alcohol and aldehyde to form a carboxylic acid. And since carboxylic acids are the most oxidized functional groups, you can reduce them to primary alcohols using LiAlH4, so lithium aluminum hydride. So if you take a primary alcohol and you use LiAlH4 on it, you can reduce it to primary alcohol. So this is the reverse reaction of creating a carboxylic acid. So when you use a strong oxidizing agent, you can turn a primary alcohol into a carboxylic acid. But when you react carboxylic acid with a strong reducing group, you can reform the primary alcohol. This functions as a nucleophilic addition of hydride to the carbonyl. So you add hydrogen to the carbonyl until you form water, and then that reforms the primary alcohol group. Other reducing agents like sodium aluminum hydride, it's not strong enough to reduce carboxylic acids to primary alcohols. So if you simulate, like for oxidizing agents, if you see a lot of oxygens in that reagent, you can use it as like a rule of thumb. Oxidizing agents have a lot of oxygens. For reducing groups, usually you can tell it's a reducing group if it has a lot of hydrogens attached to it. So you can see for this lithium aluminum hydride, you can see there's 4 hydrogen atoms attached to it. So that's the reduction of carboxylic acids. So next, I'm going to go over decarboxylation. So this is when you lose a carboxyl group as carbon dioxide from a carboxylic acid. And you can do this with 1,3-dicarboxylic acids or beta-keto acids. So if there's a carbonyl group 2 carbons away from the carboxylic acid, it can spontaneously decarboxylate when heated. So as you can see here on the bottom, this beta-keto carboxylic acid, when you heat it up, you can decarboxylate the carboxyl group as carbon dioxide from the molecule. And this works with 1,3-dicarboxylic acids as well. So if it wasn't just a carbonyl group, if this carbonyl group was a carboxylic acid, you could decarboxylate either of the carboxylic acids. So this is decarboxylation of carboxylic acids. Any questions before I give you guys a problem? I see Opal.
Yes,
you need a beta carbonyl because it forms like a 6-membered ring structure that needs a carbonyl group in the beta position. You don't really need to know like the specific mechanism that it goes through, but it's wise to know that just it has to have a carbonyl group or carbonyl group in the beta position. So whether a ketone or another carboxylic acid.
So the beta position is 2 points away from the double bond. Where is the beta position?
So as you can see, beta. So there's you number the carbons. You name the carbons via like alpha or beta. So the carbon right next to the carboxylic acid, that would be the alpha position, and then the beta position would be the carbonyl group. So
Okay.
if you look on the left side, the carbon attached to the red carboxylic acid, that's the carbon attached to carboxylic acid. The one to the left of it, so the one that's connected to the blue, the black and red line, that would be the alpha position, and then the beta position would be the carbon attached to the R group, and the carbonyl in the black color.
Okay, thank you.
No problem. Any other questions? Okay. All right. I'll give everyone this problem. Which of the following is not capable of oxidizing a secondary alcohol to a ketone? Let me start the poll. Okay. All right. I'll give everyone a few minutes for this. Okay, I'll give everyone a few more seconds for this. We want to get your answer in. Okay, I'm gonna stop the poll now. And everyone chose choice C, and yep, that's the correct answer. So choice C, lithium aluminum hydride, it's a reducing group, and it would have no effect on a secondary alcohol, and it definitely wouldn't convert it to a ketone. While A, B, and C, those are all oxidizing groups, and they would be able to convert a secondary alcohol into a ketone. So good job, everyone. Next, I'm going to go into reactions involving carboxylic acids and using a carboxylic acid to form the other carboxylic acid derivatives. So this is formation of carboxylic acid derivatives. So all the reactions I'm going to go over are examples of nucleophilic acyl substitution. So this is when nucleophilic attack by the nucleophile forms a tetrahedral intermediate that opens the carbonyl. And the carbonyl can reform again by kicking off the leaving group if it is a good leaving group. So the overall reaction is the nucleophile replaces the leaving group of the acyl derivative through an SN2 reaction. And for carboxylic acids, the leaving group is a water molecule. So on the bottom, I just have the general mechanism for nucleophilic acyl substitution. So the nucleophile attacks the molecule through a backside attack that pushes the electrons onto the oxygen. And this just forms this tetrahedral molecule. But then you reform the carbonyl by resonating down the lone pair and kicking off the leaving group, which in the case of carboxylic acids is a water molecule. So that's the general structure, general mechanism of a nucleophilic acyl substitution. And next, I'm going to go over how to form an amide. So for amide formation, what happens is the ammonia NH3 or an amine attacks a carboxylic acid and forms an amide. So as you can see on the bottom, the carboxylic acid, when reacted with a ammonia molecule or an amine, it's able to form this structure on the right called an amide. So this is how to form an amide via a carboxylic acid. And this is through nucleophilic acyl substitution. Next, formation of an ester. So when you react a carboxylic acid with an alcohol group under acidic conditions, this forms an ester group, also known as esterification. This is considered a condensation reaction because you combine two groups and form H2O as a side product. So on the bottom, as you can see, when you take a carboxylic acid and you react it with an alcohol group, you can form this ester group on the right. So it's a carbonyl with this alcohol group attached, and you form H2O as a side product. You can also convert the ester group back to a carboxylic acid and alcohol through a hydrolysis reaction. So that's the opposite reaction when you use the water to cut this ester group back into a carboxylic acid and an alcohol. And it makes sense that this reaction is faster with primary alcohols because there's less substituents attached to that carbon attached to the hydroxy group. So with less steric hindrance, it's able to proceed faster. So when you have a reaction with a either a secondary alcohol, primary alcohol, or tertiary alcohol, the primary alcohols are faster than the secondary and tertiary alcohols because it has less steric hindrance. So that's the formation of an ester group. Next, an anhydride. So for anhydride formation, you use 2 carboxylic acids to form an anhydride. This is also a condensation reaction because it combines these 2 carboxylic acids and forms water as a side product. So what happens is this these carboxylic acids through a nucleophilic acyl substitution reaction, you convert 2 carboxylic acid groups to an anhydride group, which is even more reactive than a carboxylic acid. So this is anhydride formation. So all 3 of those reactions were nucleophilic acyl substitution reactions, where a nucleophile attacks the carboxylic acid, and the nucleophile replaces the hydroxide group in the molecule after the carbonyl reforms and kicks off the water as a leaving group. Okay. Next, saponification. So this is soap formation. This is when a salt is formed from a long chain carboxylic acid, and after reacting with either sodium hydroxide or potassium hydroxide, so any strong base. So we take a long chain carboxylic acid and react it with a base, you form this soap molecule, and also water as a side product. So the soap that's formed, it has a long non-polar tail and a polar carboxylate head group. This may look familiar because, as you can see on the bottom, this is the formation. This is the reaction that involves a fatty acid and a base, and it forms a soap molecule. So our body does this reaction often, cutting down fatty acid groups using base to form soap and water. So that's saponification, soap formation using a carboxylic acid group. Any questions before I go on to a problem? You can put in the chat or unmute. Okay, all right, I'll move on to this question. So reacting a carboxylic acid with an alcohol group in the presence of an acid catalyst, what would you be expected to produce? All right, I'll start the poll and give everyone a few minutes for this. All right, I'm gonna stop the poll in a few seconds if you want to get your answer in. So everyone picked choice B, and yeah, that's the correct answer. So when you take a carboxylic acid and react it with an alcohol and using acid catalyst, that would form an ester group. So just remember, if you react carboxylic acid with an alcohol, it would form an ester group. For choice A, an amide, you would need either ammonia or amine group, an amine group. For ketone, you would have to reduce the carboxylic acid. Similarly for secondary alcohol, that would take a lot of work if you want to form that, but you would have to reduce it as well. So yeah, choice B is the correct answer. And yeah, that's all I have for everyone today. Anyone have any questions regarding the lecture? Did kind of go through everything pretty fast. If you wanna ask any questions, just let me know. Opal said, is Jones reagent a new thing? I'm not sure what you mean by new thing. Jones reagent. Jones oxidation, yeah, so Jones oxidation, I don't believe it's a new thing. I did learn it when I was taking orgo. It's not something you really need to know in detail. Just need to know that using the Jones reagent, it oxidizes it into oxidizes alcohols into carboxylic acid. Grignard's reagent, it wouldn't really that's more for like carbonyl groups. So Grignard's reagent, it's used for like ketones and aldehydes. Does that make sense, Opal?
Yes.
Yeah. Any other questions? Next week, I'm going to go over more in detail like aldehyde groups, ketone groups, and the other carboxylic acid derivatives. Thank you everyone for coming. Sorry about that little fiasco earlier with the login. If you have any questions, just put it in the chat or unmute and I can try to help you out. Okay. All right, if no one has any questions, I'll end the meeting here. Thank you everyone for attending. Thank you, Chris, for helping out. All right. Have a good night, everyone. Thanks, Chris.